And in order to complete the proof, first we need we want to see that this statement holds for every divisor. As a first step, actually not the first step, but to see that it holds for every divisor, first we need to show that for every divisor A, there exists divisor A1 and D, and positive natural number, S prime, such that divisor A1 is bigger than or equal to A. First, we show the existence of such a divisor, which is equivalent to D, and D is less than or equal to S prime times B. So it's a bit complicated statement, but if we are able to show that, then if we consider the degree A minus the dimension of A, and if such a A1 exists which satisfies this inequality, then we know that its degree minus dimension is bigger than the degree and the dimension of A. We can call it by start this statement. And if such a divisor D exists which is equivalent to A1, we know that their degrees and the dimensions are all also the same by corollary 1.4.12. And if this satisfies such a divisor satisfies this inequality, again by star, we know that the degree of D minus L of D is less than or equal to the degree of S prime P and the dimension of S prime D. And as we have seen here, this statement, this inequality holds for every S and for every divisor which is of the form S times P. Then by double star, we can see that this is less than or equal to the constant gamma we considered before. So in this case, it will be enough to show that to prove to complete the proof, it will be enough to show that this claim is true. And for this purpose, for a given any divisor A, let me mention that we can choose a positive divisor which is large enough with respect to partial order. And for the positive integer S, let me also observe that the divisor SP minus A1 is less than or equal to SP. Again, by lemma 1.4.A, we know that the S space of SP minus A1 is the S space of SP. Then the dimension of L of SP minus dimension of SP minus A1 is less than or equal to degree A1, because the degree of the differences SP minus A1 and the SP is equal to the degree of A1. And if we remove the degree A1 to the left-hand side and this term to the right-hand side, we see that L of SP minus degree of A1 is less than or equal to dimension of SP minus A1. And for the dimension of L of SP, by the double star, we know that SP, degree of SP, S prime B and dimension of S prime B is less than or equal to gamma. So that means this term is greater than or equal to degree SP minus gamma and minus degree of A1. And here in this case, okay, this can be positive term or negative term, but we know that the B is a positive divisor because this is the pole divisor of F. And if we choose as this natural number is sufficiently large enough, we can guarantee that this quantity is always bigger than 0. So that means we can choose as sufficiently large such that we get this inequality. And until this step, we show the existence of A1 and the divisor A1 and the S prime. And to see the existence of D, which is equivalent to A prime and less than or equal to S prime B, first, let me observe that this dimension for sufficiently larger dimension of SP minus A1 is bigger than, strictly bigger than 0, so that means there exists a non-zero function inside of this Riemann row space. That means principal divisor of this function is bigger than of SP minus SP plus 1. And by setting A1 minus Z, first by the equivalence of the divisor, this is obviously equivalent to, this divisor is equivalent to A1. And this divisor D is less than or equal to A1. And if you consider this inequality, so that means minus that is less than or equal to SP minus A1. Indeed, we show the existence of the divisor D, which is less than or equal to SP. And this completes the proof of the claim. And thanks to this claim, now we know that this statement holds for every positive degree divisor. Indeed, for every divisor A. And with respect to this, I mean, with respect to this upper bound, we have considered, or we have considered for the lower bound for the dimension, or the difference between the degree and the dimension. Now we are ready to introduce one of the most important notion, the genus of the function field f. And this will be quite abstract definition, and indeed, for the moment, it will tell nothing about computational aspect. However, this definition, let me note that this definition makes sense thanks to proposition 1414, because we always know that this quantity bounded above gamma for a constant gamma. So that means there exists always the maximum of such a set over all divisors. And actually, for the computation aspect, we will see more statements how we can compute the genus, or this is actually huge concern in the theory, because this is also important. It gives us the characterizations of the function fields depending on the genus, and it will be also important when we compute the parameters of the, for instance, algebraic geometric cos. But for the moment, let me give some easy observations. The first one, this quantity is a non-negative integer, and I'm sorry to forget to say that this quantity also depends on the function field. Sometimes we also use the notation of g of f, and to see that it's a positive integer, in the previous definition, let me consider the divisor, zero divisor. Then degree 0 minus L of 0 plus 1 is equal to 0. And G is the genus defined as the maximum of the oldest quantity. It's obviously bigger than or equal to 0. And to compute, as I mentioned before, to compute the dimension and the genus will be one of the main concerns. And as a first step, we will understand this relation more explicitly when we see the statement of the Riemann-Roch theorem. But as a first step, for the moment, I only want to give the statement of the Riemann's theorem, or theorem 1.4.17. If we consider a function field of genus G with respect to this definition, then for all divisors A, its dimension is bigger than or equal to their degree plus 1 minus G. And we see that there exists a constancy only depending on the function field. Then instead of inequality, we are able to get the equality in this statement if the degree of the divisor is in some sense sufficiently large enough. Next week, we will begin the statement of this theorem, but for the moment, just let me finalize this lecture with an observation. For statement A, actually, we can provide this inequality by using the definition of the genus, because genus is defined as the maximum of this number over all divisors. So genus is always bigger than or equal to degree A minus L of A plus 1 for any divisor A. Then that means we always get this inequality. And to see the existence of such a C, we will in some sense follow the similar proof with proposition 1.14. So this is all what I want to say, and see you next week.